Welcome to the next lecture on microwaves. Now we are going to start formally the rectangular waveguides. As you can see, let's see the pictorial view first. These are the real pictures of some waveguides. What is a waveguide? It is a simple metallic tube. It is a hollow tube which can have rectangular shape or circular shape, which is used to guide an electromagnetic wave. As an example, let's say that if you see the optical fiber, you can think of optical fiber as a waveguide for light, visible light. In the same way, at microwave frequencies, waveguide is a similar type of carrier. Okay, the way optical waves or optical signals are transmitted via optical fibers, waveguides are analogous to the optical fibers at microwave range. As an example, suppose I am using here a terminology X band, which is the military frequency band, 8 to 10 gigahertz. The dimensions are like your width is 2.286. These are the inner dimensions. As you can see in these waveguides, you have so it is in hollow, so there will be inner dimension. Okay, so like this, inner dimension, and there will be the outer dimension. Okay, so inner height and outer dimension, outer height. And usually it is of two types, rectangular and circular. So here is the circular one. Okay, this one. And in this particular figure, you can see that there can be even variants also. So here are different shapes, and some of them are some different particular devices, like there are some directional couplers which we will also study. Now our main aim in this lecture will be, if we transmit any microwave at one end of this waveguide, what is the relationship of frequency? I mean, which frequencies will it allow? Will it allow any frequency? We will see that after solving the Maxwell equations. Definitely we have to solve Maxwell equations when we are transmitting electromagnetic waves through these waveguides, that it is not that for a given dimension of waveguide that any signal will be transmitted. So depending upon the dimensions, there will be particular frequencies which will be allowed to transmit through the waveguide. So these will be called dominant modes. Okay, so the modes we call the frequencies which are allowed through the waveguides, and dominant mode will be the one. Basically, there will be a cutoff frequency, right? That below this frequency, no electromagnetic wave will be will get transmitted through the waveguide, and that cutoff frequency will decide the dominant mode, so-called mode. We will see that terminology. Now to start with, we will start with a rectangular waveguide because of its simplicity, and definitely for rectangular waveguides we will use a rectangular coordinate system, quite obviously. So here is, I will draw this. So this is the y, this is the x, and the z axis. So now we will recall what are the wave equations which we basically derived from Maxwell equations. These are the two wave equations. One is for electric field and the other is for magnetic field. E is the electric field intensity, H is the magnetic field intensity, and you know what gamma was derived last time as, and we can represent this gamma as alpha plus j beta. These two equations are also called vector wave equations. So definitely here the Laplacian operator del square will be written in rectangular coordinates because of the symmetry. Okay, right now we are into rectangular we are studying the rectangular waveguide. So unnecessarily, if you here use cylindrical coordinate system or spherical coordinate system, will complicate the problem. So we will use rectangle. Now we can see that these equations are written in vector form. We will first study the scalar form. Suppose if you see electric field, it has definitely three components, Ex, Ey, and Ez. So these equations will then degenerate into scalar equations, three scalar equations. So let's first see a general equation where let psi be a scalar, some scalar function. Then in scalar form we can write the equation as del square psi is equal to some gamma square psi, or in rectangular coordinates it is del 2 psi upon del x2, del y2 and del z2. This equation is very famous in partial differential equations. It has a special name, it's called Helmholtz equation. So we will first try to find the solution of this equation, and one of the so this is there are some comments. So this is a linear differential equation, and in addition to being linear, it is an inhomogeneous. Linear because there is no square term like del upon del x square or del 2 psi upon del x2 whole cube. So these are non-linear, so there is no such term, so it is a linear. And what homogeneous equations are, as an example, suppose you have f1 of xy dx is equal to some f2 of xy dy, okay, and which finally can be written in this form. Suppose some dx upon x is equal to some phi of t dt, okay, after substitution. If we can write any equation in this form, so that now we can easily integrate the both sides, such an equation is called a homogeneous equation. And here we see there is nothing like that, so these are inhomogeneous partial differential equations. We can't directly write it in a way like then we integrate both the sides to get the solution. We need to do something. So one of the methods to solve such a partial differential equations, especially the Helmholtz equation, which is very famous in solving the wave equations even other than in electromagnetic waves, that's called method of separation of variables. In method of separation of variables, we assume that the solution, so to assume what solution should be, we assume that the coordinates, suppose if you have electric field variation, the x field variation, the variation of electric field along x component is in some sense independent of variation in y component and z component. So we assume that the solution psi, okay, as a function of x, y and z. So what can be a general solution? So general solution can be any function of x, y and z, but we assume a particular form wherein the x terms are separate, the y terms are separate, the z terms are separate. I will give an example. Suppose as an example, if I write psi is equal to sine of 2 pi fx e to the power minus some by log of cz. So we can see that we have written, well, I can represent this as x of x, this is only function of x, this only function of y, this only function of z. So this is one way of representing psi. The other example of psi can be, suppose sine of 2 pi xy, okay, e to the power minus zx, right? So here this cannot be represented as separate functions. We can't represent it in like x of x, y of y, because sine of 2 pi xy is function of both x and y. So we assume that such solutions are not possible. Only this type of solutions are possible. So we are representing psi as x of x, z of z, okay. Now we will differentiate partially with respect to x, y and z. We get, since y and z don't depend on x, so they remain as it is. I will drop the small y and small z for convenience, and partial derivative with respect to x. Similarly, del psi upon del y will be, and del psi upon del. Now let's take second derivative with respect to x here, okay. So again, y and z are not functions of x, so they are constant with respect to x. So del 2 psi upon del x2 will be yz del 2x upon del x2. Similarly, we can find del 2 psi upon del y2 and del 2 psi upon del z2. Now we substitute these three values in the differential equation. We get this equation. Now we divide both sides by 1 over x y z. We will get the following differential equation, right? Now I will drop the partial sign, because if you look at this term, first of all, x is function of x only, y is function of y only, z is function of z only. So I will write 1 over x d2x upon dx2. Similarly, other terms. Now here we use one argument. You see, we have here three terms. This is only function of x, this is only function of y, this is only function of z, right? And this gamma is a constant. You are adding three independent terms. They are in some sense independent, okay? Because this does not have any term on y, so that it depends on second term. This does not have any x or z term. This does not have any x or y term. When three terms which are independent, they are getting added up and equal to some constant, then each individual term should also be constant. So it must be constant, okay? Now let us represent those constants by kx, ky square and kz square, okay? And for some reasons which you will see soon after the solution, we take each of these terms to be negative. So for that, we will write this gamma square is some minus kx square plus, then minus ky square minus kz square, okay? So hence each of the term 1 over x d2x upon dx2 is equal to minus kx square times or minus kx square, which implies that it is equal to minus kx square x, okay? Similarly, d2y upon dy2 is minus ky square y, d2z upon dz2 is minus kz square z, okay? So these are our now three equations, and the solution of each of these is very well known. It is a second order differential equation which has sinusoidal solution, okay, which you have studied already. So we can represent x as a sine kx of x plus b cos kx of x. A, b are constants. They will be determined by boundary conditions. Similarly, y is equal to c sine ky of y plus d cos ky of y. Similarly, z equal to sine and cos, like this. So total solution of Helmholtz equation in vectorial coordinates will be psi is equal to this a times sine, I will write obviously the product of these three functions, okay? An important comment here is this gamma, which is the dielectric constant. We call it intrinsic dielectric or propagation constant. Sorry, not dielectric, propagation. And we have derived it that it is given by under root of j nu omega into sigma plus j omega epsilon, right? But we know that we have made the convention in such a way that wave is propagating in z direction, right? So we need a propagation constant in the direction of wave propagation. We call that gamma g. That's called propagation constant. Propagation constant. After we confine the wave to the waveguides, okay. Now, how will we get that? We know that gamma square is minus kx square minus ky square minus kz square. So if we write like this, gamma square plus kx square plus ky square, which is minus kz square. So this minus kz square, this will be our gamma g square. It is in the direction of z. Okay, so we can write then gamma g square is gamma square plus kx square plus ky square, and we write this kx square plus ky square as something called kc square, where this kc is obviously under root of kx square plus ky square. It is called cutoff wave number. Cutoff wave number. The reason for calling this will be clear soon when we will define the cutoff frequency. And let's consider the lossless dielectric. In lossless dielectric, sigma is 0, so gamma will be, so in this equation you put sigma equal to 0, so gamma will be or gamma square will be equal to j nu omega times 0 plus j omega epsilon, which will be minus omega square mu epsilon, and hence gamma g will be equal to gamma g square will be equal to gamma square, that is minus omega square mu epsilon, and minus kc plus kc square. Okay, and we will write it as minus of omega square mu epsilon minus kc square. Okay, so you will see this, we want gamma to be complex. See, if gamma is not a complex, you will see later on, then we will not get the sinusoidal waves. Yeah, sorry for inconvenience. So then I will write gamma g as, since there is a minus outside, when I take square root of this, okay, there will be the imaginary term will come here, j, of course plus minus, under root of omega square mu epsilon minus kc square. Okay, see, you should recall one fact if you have done partial differential equations, especially the wave equation in your second semester also, that if you have suppose d2y upon dt2 is equal to some constant times y, right? You will see that if this constant is positive, we will get damped waves, we will not get the proper waves. This constant should be negative for this type of equation to have a sinusoidal solution. Okay, that is why we demand these to be negative, okay, so that its square root is imaginary or complex in general, right? Now there will be several cases with regard to this propagation constant. Case 1 is quite obvious. Case 1 is when there will be, suppose if gamma g is 0. So gamma g 0 will means that there will be no wave propagation in the guide. This is also called evanescence case. Okay. So when will be gamma g equal to 0? When omega square mu epsilon will be equal to kc square. Right? So with this condition we can derive something called cutoff frequency. Okay, so the omega at which this happens, let's call that omega c, which is equal to 2 pi fc, where this fc will be now the cutoff frequency. Okay, because if your fc, you will see that if your fc is equal to this, it will not be propagated, it should be greater than this. So this will be equal to, so we can write omega c can be written as kc divided by under root of mu epsilon or fc will be equal to 1 over 2 pi under root nu epsilon under root of kx square plus ky square. Okay, this is one case. What will be the other case? Case 2 will be when there is a propagation. So when there is a propagation, we will need omega square mu epsilon minus kc square should be positive. See, remember that we want gamma g square to be negative, hence gamma g should be imaginary for propagation to happen. Now for that to be imaginary, the term inside square root should be positive, right? So this will give us condition omega square mu epsilon should be greater than kc square. Okay, and the propagation constant, in such case we know that our gamma g, which was represented as alpha plus j beta, now because sigma is 0, it is a lossless case, so alpha is 0, so it is only j beta g. I will represent as g. Okay, and which is also equal to, we have seen just now, it is plus minus j omega plus minus j under root of omega square mu epsilon minus kc square. We just saw it. Okay, so now what is this kc? If you see, the kc is related to the cutoff frequency of case 1. Okay, actually we can write, if omega c, which is 2 pi fc, is the cutoff angular frequency, then kc square is equal to omega c square mu epsilon. So kc corresponds to, that is the reason we call it kc, it corresponds to the cutoff frequency omega c. Okay, so I can write this gamma g as plus minus j under root of omega square mu epsilon minus omega c square mu epsilon, which I can also write as, so I will take omega out and under root of mu epsilon out. What remains inside is 1 minus omega c square divided by omega square. Okay, or which can also be written as plus minus omega under root mu epsilon under root of 1 minus fc by f whole square. Okay, so it means that the operating frequency, which is your f, must be above the cutoff frequency in order that waveguide gets transmitted, because if f will be less than fc, then the inside term will be imaginary. It is here j. We want gamma g to be imaginary, remember, because we want gamma g square to be negative. Any number will be negative only if its square root is imaginary. For that we want this thing. So this is the now notion of cutoff frequency. So f must be greater than fc. So if you transmit a any wave, electromagnetic wave via a waveguide, it is not necessary to get transmitted unless your frequency is above the cutoff frequency. Okay, similarly there will be case 3, that now what if actually the cutoff frequency, or in other words this omega square mu epsilon, which we assumed till now should be greater than, if it is less than kc square. Okay, then you see what will happen. Your gamma g, if we write it, if we use the same equation, okay, so it will be here plus minus j omega under root of mu epsilon under root of, I will write here 1 minus fc by f whole square. But now the inside term, because omega square mu epsilon is less than kc square, so the inside term is less than 0, so I can take one more j out and then write fc by f square minus 1, right? So this I can write now as plus minus j square under root of mu epsilon under root of fc by f square minus 1. J square is minus 1, so it remains same, minus plus In this case, you will see the gamma g is not imaginary. So gamma g square will be positive. And we know that if you have a differential equation, d2y upon suppose dt2 is equal to some alpha times y. If alpha is greater than 0, this equation will have damped type of solution. Okay, it will have exponential decay, the solution of this equation. It will not be sinusoidal at all. Okay, so this is the case when the wave will be attenuated. Right now, we have derived the general equation, and we will after this see something called, there are different modes in rectangular waveguides, and actually how these constants ABC are actually identified using boundary wave conditions, right? And also we will see the kx, ky, till now they are merely a constant, how they depend upon the geometry of the waveguides, that we will see in the next lecture.